Okay, so semester one final exam review, chemistry is study of the composition of matter, meaning what is matter made up of, whether we're talking about atoms or whether we're talking about um, compounds or whatever we're talking about, what's within it, what makes up matter, the matter that we see, matter that we sense all the time. Units are basically standards or ways of making measurements. So it depends on the type of measurement we're doing. If we're doing some kind of mass measurement, um, we'd use grams, volume, we might use milliliters or cubic centimeters. The manipulated variable is what we are testing. So what we are testing in an experiment. So if it's what we are testing, we choose to change it. So something that we're changing. And in an experiment, we want to keep everything the same except for the one thing that we are trying to test. I gave an example in class of my route to school, which is the fastest way to get to school in the morning. Um, so I have a couple different options I can take. And the thing that I'm changing is the route. Now, as a result of changing the route, the amount of time it takes to get to school might be different. And so that's the responding variable. So this changes because of the manipulated variable. It's also important to remember with these when we do graphing and whatnot, we always put the manipulated variable on the x-axis, and we put the responding on the y-axis. Where we had that dry mix statement we used in class. The dependent or responding variable goes on the y. The manipulated, also called the independent, goes on the x. Control, I was thinking with control, keep the same. And I told students, so you could kind of think of this as constant because I was seeing this here. But really, control group, you can kind of think of normal conditions. So if we want to see if something's different than normal, we might have a normal group, a control group, and then we might change something in another group and see how the results are different. Matter is just going to be the amount of stuff in an object, which we call that stuff matter now. So the amount of matter in an object or in a substance. Okay. And conservation of matter. Matter can't be created or destroyed. And since matter is the amount of mass, the starting mass has to be equal to the final mass. Whether we're combining things or whatever, we can change things around, whatnot. We can rearrange things, but the beginning mass should always equal the final mass. Now, then we talk about open and closed systems, where maybe that's not always the case, but it's not that the matter is being created or destroyed. It just might be entering or exiting the system that we're focused on. Okay, so we can have chemical changes where we make new things, make new substances from starting substances, rearranging particles in terms of their attachments. So we're making something new or different, all right? But physical, from beginning to end, it's the same substance. So it's just a change in size, shape, or phase. So I was talking in class how if we have ice, ice is really a compound H2O. It's in the solid phase at that point when it's ice. If we melt it, it becomes liquid water, but it's still H2O. It's just now in the liquid phase, so it's still the same substance. If I took a piece of paper, it's paper. If I rip it in half, it's still paper. So that would just be a physical change in size or shape. Um, so when we talk about conservation of matter, one area where we might have a difference between the beginning mass and the final mass might be if we have an open system, because in an open system, matter can enter or exit the system. So if I'm boiling water and I just want to say, okay, I'm going to boil water and I have the initial mass of this liquid water and I'm going to boil it, and because of conservation of matter, at the end, um, the final mass of the water should be the same as what it was before. But we know that really when we boil water, some of the water, liquid water, is changing into gas water, which we call water vapor, and water vapor is going to be less dense than the liquid water. So it's going to go to the surface and it's going to leave the water. It's going to go out into the air. It's not being destroyed. It's still molecules of water. They're just now going into the gas phase. And they're going into the air, so they're leaving the system. So if all those molecules that left, all that matter that left, and then we take a final mass, it's reasonable to understand that the final mass is going to be the same, or sorry, the final mass is going to be different than what we started with. It should be less because particles left. Now, if instead I boiled it and I had a closed system, so I covered the top or something, um, that would be a closed system. So matter cannot enter or exit the system. So in this case, with the closed system, starting mass should always equal the final mass in this case. Right? And so mass is the amount of matter in an object. With the matter up there, I should have said, by the way, that matter, anything that has mass and takes up space. Sorry, should put that up there. But mass, the amount of matter in the object. That's it. How many particles are in there? That's all we're looking at. Typically, we would use a balance to measure the mass. The units we're going to use are grams, which are abbreviated G. We could have milligrams for smaller ones. We could have kilograms for larger things. Temperature is really the average kinetic energy of particles. And we know that kinetic means moving, so really we're talking about the speed of the particles. And so we could use a thermometer for this, which typically we use degrees Celsius. Later we can convert that to Kelvin. All right. Pressure is force per unit area, like say pounds per square inch maybe. It's caused by particle collisions. Some units, we had a lot of different units for this. ATM, atmospheres, kPa. We had torr, we had millimeters of mercury, and we even had PSI for that. Forget anything. So volume is the amount of space something takes up. And now we can do this some different ways. We could do it with a graduated cylinder, if we're dealing with like a liquid, so typically liquids we put in a graduated cylinder and find their volume, how much space they take up, in which case the units would be mLs, milliliters. We could even use a ruler if we had a regularly shaped object and multiply three sides, like length times width times height, and then we would get centimeters cubed. Some different options there. There's another question later in the review where we'll talk about that. The density is mass per volume. All right. So air pressure is pressure caused by air or force caused from air particle collisions with each other and other things. When we talk about pressure, we keep talking about the number of hits. Direct relationship means um, both variables that you're looking at in a relationship, both variables, like on a graph, you have a manipulated variable and a responding variable. Both variables change the same way, okay? So one variable goes up, so does the other. Or one variable decreases, so does the other. So what happens is on a graph where we go left to right, where we have our manipulated variable and our responding variable, it's always going to go uphill, okay? And inverse relationship, same thing. We're looking at two variables that maybe we could graph with each other. But in this case, the variables go in opposite directions. So if you increase one, the other decreases. If I decrease one, the other increases. So what happens with that is if I do a graph of manipulated and responding variable, it actually goes downhill. And it could have a curve to it, but the point is it's going downhill as you go left to right. Okay. Accuracy, how close your result or results are to an expected result. Okay. Precision we kind of use interchangeably a couple different ways, like how precise is an instrument, meaning how many decimal places can we go down to, how tiny is the measurement. Precision can also refer to how closely grouped results are. So if all your results are all close together, that's high precision. If they're all spread out on a graph, that would be low precision. Meniscus, okay? So you guys have seen us, we did measurements with graduated cylinder, and what happens is liquids tend to attract a little bit to the sides of the container, and what it causes is a little depression in the middle of it. So this is the meniscus, and what we do is we always measure from the lowest point. All right, condensing. Condensing is when gas cools, so the particles move slower, which means it turns into, so the gas cools and turns into a liquid. So water in the air during the summer. It's nice and warm during the day. Particles are in the air as water vapor. Okay, that's water gas. We call water vapor. It's in the air. At nighttime it cools, and when it cools, those particles will condense on the grass. So that's why if you go out in the morning in the summer, A lot of times the grass is wet. That's because the water vapor condensed into liquid water on the grass. Kinetic energy is moving energy. So we think of kinetic energy with speed, particles. Okay. More kinetic energy means faster. Less kinetic energy means slower. Constant, these are the things in experiments that do not change, or they stay the same. So we have Boyle's law, Charles' law, Gay-Lussac's laws, which all are relationships between different things. Really, Boyle's law is a relationship between volume and pressure. And we know just by kind of reasoning that this is an inverse relationship. But I did say we don't have to necessarily know the name of it, but we should know that volume and pressure is an inverse relationship. Charles' law is a relationship between temperature and volume. Okay, we should know that this is a direct relationship. So if we increase the temperature, the volume will also increase. Or if we decrease the temperature, the volume will decrease because particles won't be hitting the sides of a container as often, which will be creating a temporary lower pressure, causing the sides of the object, if it's in a has to be in a flexible container so that the volume can change. But again, you don't have to know Charles' law. Okay, you don't have to know that that's the name. And then we have Gay-Lussac's, which is a relationship between the volume and the temperature. Okay, so in Gay-Lussac's law, this is also a direct relationship. So we're not changing the volume here. Volume stays constant. And then the other ones, if something wasn't mentioned, like Charles' law, we didn't mention the pressure. So the pressure must remain constant from beginning to end. Now, like I said, with Charles' law, there's slight changes that cause the sides of the container to change. But your beginning, the pressure in a flexible container, internal and external, is going to be equal at the beginning and end. There will be a little change in between, but beginning at the beginning and end will be the same. Internal equals external for pressure. Okay, so some people on the quiz or test, they said they stay the same, but it's not that they stay the same. The pressure internally and externally in a flexible container are always equal. We can have different external pressures, but if it's in a flexible container, that external pressure is always going to be equal to the internal pressure. So with Gay-Lussac's law, it's a relationship between volume and temperature where the volume is constant. So this is, when the volume is constant, it means it's a non-flexible container. That means the sides do not move. It's rigid. So if we have a gas in a rigid container and we increase the temperature, I wrote the wrong thing here. Sorry. It's a relationship between pressure and temperature. So if I increase the temperature, the pressure is also going to increase, because if I increase the temperature of the particles inside a container where the sides can't move, the particles are going to move faster. And they're going to hit the sides of the container more often. And how often they hit the sides of the container, that's pressure. Higher pressure, more collisions. Lower pressure, less collisions. All right, absolute zero is on the Kelvin scale. In the Kelvin scale, it is 0 Kelvin. This is the lowest possible temperature, because at this temperature, particles would theoretically stop moving. So we know that as we cool particles, they move slower and slower and slower and get closer and closer and closer together. So theoretically, if we kept cooling something, cooling it, cooling it, cooling it, eventually those particles would slow so much that they would stop. And that's 0 Kelvin, which we call absolute zero. it's equal to negative 273.15 degrees Celsius. So that's the lowest possible temperature. Okay. Endothermic and exothermic, um, just to talk about them, energy would be going into a system, so we're adding energy. And with exothermic, energy is leaving the system. Energy like heat, for example. That's typically what we deal with. I always say like exo, like exit, energy leaves. Endo, energy comes in, so energy goes in the dough. All right, so questions that we have here. I already addressed this a little bit, but I'll do it again. A piece of a lab equipment that we use to measure mass is called a balance or electronic balance. And what units would we measure in? That would be grams, which we abbreviate G. Lab equipment used to measure volume, we use, depends, okay? So let's talk about solid and liquid, okay? I guess we can talk about gas too, gas pressure, gas volume. Yeah, let's leave that out. So solid, it depends on the solid. Like we could measure three sides, do length times width times height, which would give us units called centimeters squared. So that's using a ruler, okay? But sometimes we have solids that aren't regularly shaped. And the solids that aren't regularly shaped, like it doesn't have three regular sides, we find the volume of those the same way as liquids. We use a graduated cylinder. And if we use a graduated cylinder, we're probably going to be dealing with units like mLs, milliliters. All right, what piece of lab equipment would you use to measure temperature? That's the thermometer. That's going to tell us degrees Celsius. Like I said, we can later take that and add 273.15, which would give us Kelvin. All right. Pressure, we could use a barometer to measure pressure, maybe in millimeters of mercury. We can also use a gas manometer, dealing with different pressures on one side or the other. We had all those different units for pressure that we mentioned that we can still deal with, that I mentioned earlier on the video, like atmospheres, kPa, torr, all those. All right, so these are all density problems. So we got to use this general equation where the density equals the mass divided by the volume. Okay? Density equals mass divided by volume. All right, so this equation's great as long as I'm solving for density, which I am in A and C. In B, we're going to have to do something a little different because it's in mass. All right? Mass is what we're trying to solve for. So all I have to do for density is take the mass and divide by the volume. So for density here, I'm just going to take the 42.751 grams, and I'm going to divide that by 22.61 milliliters. All right, so I have 42.751 grams divided by 22.61 milliliters, and the answer comes out to be 1.89. So round off to a couple decimal places. If we were being careful about significant figures, it would actually be 1.891. You're not responsible for knowing that on the exam, though. So we're looking for something like this, 1.9, 1.89, 1.891. And then the units, since we did grams divided by milliliters, it's just grams divided by milliliters. Those are that's a typical unit for density. If the volume was in cubic centimeters, I might have grams per cubic centimeter, but same idea. Okay, and then the letter C, all I'm going to do is take the 123.622 and divide by 35.95. So 123.622 divided by 35.95, and I get 3.44 or 3.39, something close to that. And again, I had grams divided by milliliters, so that's the unit, grams divided by milliliters, grams per milliliter. So now on letter B, what I have to do is it's asking me to find the mass. I have to rearrange this equation. I have to find a way to solve for this. All right? So density equals mass over volume. And I want to solve for mass. So what we have to do is make sure, first of all, the unit we're trying to solve for is on top of the equation, on the top portion of the equation. It's not in the denominator, all right, which it's already on the top, so that's good. It's right there. The second thing we have to do is make sure it's by itself. And right now it's not by itself on the right side, or whatever side it happens to be on at the time. It's being divided by volume. So if I want to get it by itself, all I have to do is do the opposite. If it's being divided by volume, I'm going to multiply it by volume, okay? Because when I multiply it by volume, that will cancel volume out and get rid of it. But the rule is, if I'm going to do that to one side of the equation, in order to keep it the same equation, I have to multiply both sides by volume. Get rid of this so it's not confusing. All right? So really, the formula for solving for mass becomes volume times density equals mass. So now that I know that, I can just put those numbers in the equation. So the volume's 23.1, and the density is 2.1, so I'm just multiplying those two numbers together. 48.51 is my answer. And so what happens during that equation is really I've got centimeters cubed on top and on bottom in that equation is what happens. And so if that happens, those units end up getting canceled out when I do it, and the only units I would end up with are grams, which is what I need for mass. All right? Okay, and then we've got number 6 here. And with number 6, density is a property of a substance. So it's something specific to a substance. It's something that helps us identify the substance. So I can't use like the mass. Hey, look, it's 25 grams. It must be nickel. Because I could have all sorts of different masses of nickel. Look at this. We have 2 liters of water. Does that mean that it's water because there's 2 liters? No, because I could have 4 liters. I could have 10. I could have 20. I could have 1,000. But what is important is the density, and they say at room temperature, so a specific temperature, because we know the densities can change with temperature. The particles will start to spread out. But at room temperature, I can say the density is a property because whether I have, let's say I have a chunk of copper, and let's say this is how the particles are arranged in copper. They're this far apart. This is the density of copper. Even if I took a smaller part of that, the particles would still stay in the same spacing, which really the spacing is the density. They would stay just as far apart. That wouldn't change. So what happens is I can identify things based on their density at room temperature, like water. We talk about that a lot. So water is 1 gram per milliliter. That's its density at room temperature. So if I had a clear substance I was trying to identify, I might check out things like its freezing point. Is the freezing point 0 degrees Celsius? I might look at, is its boiling point 100 degrees Celsius? Is it transparent? Can I see through it? But I could also look at the density, measure different masses of water and make sure they match up to the milliliters, which would mean that the density is 1 gram per milliliter. That means it's water. All right, and then number 7, this is a conservation of matter problem. So I have 2 coppers to start with. I have 2 oxygens. So starting, before I make any changes, like I said earlier, chemical change, I can rearrange things, that's fine. But if I have 2 coppers and 2 oxygens, and I rearrange them, I shouldn't have an extra 2 of each appear. That's wrong, because this looks like they're just appearing from nowhere. So like I was saying, this violates the conservation of matter rule. We can't have things just suddenly appear. So these cannot be there. Now if I just had 2 coppers and 2 oxygens arranged this way, sure, that's equal to what we had at the beginning. Another idea, I couldn't have 2 coppers and 2 oxygens to start, and then over here, maybe I only had 2 coppers and 1 oxygen. Where did the other one go? Okay, so conservation of matter and energy. Um, this part, conservation of matter, whatever we start with, we have to have at the end. Okay, so moving on from here. Oops. All right, so here's the idea. All right, if I take, this is more conservation of matter stuff. If I dissolve 25 grams of Kool-Aid in 150 grams of water, that Kool-Aid doesn't disappear. It's not leaving. I don't see any gases leaving or anything, so it must still be in there. If I have 25 grams of this to start, and I have 150 grams of this, and I combine them, that means at the beginning I had a total of 175 grams, and even though it dissolves at the end, should still have 175 grams. Okay. Um, Number 9, a piece of wood. So idea of conservation of matter says that if I have a piece of wood and the mass is 10 grams, it should be 10 grams at the end. Okay, but this is the thing. Whenever we have gases involved, we have to think about, is it an open system? Okay? Because if it's an open system, that mass can change. All right, so if we're just burning wood out in the open, that means we have an open system. There is a gas involved with burning something. O2 is needed to burn something. It's one of the reactants. Okay, it actually gets formed into a product that we're going to find the mass of at the end. All right, so actually in this scenario, the mass should slightly increase. Okay, because what we did was initially, you can think of it this way. This is not technically accurate, but at the beginning we had wood, okay, and we had oxygen in the air that we didn't find the mass of. But at the end, we're going to have the wood now burned, but we're also going to have oxygen with it. All right, so we're going to have more stuff that we didn't account for in the beginning. Number 10, I talked about this earlier. So we've got water, we're boiling it. So we've got all this water. All right, so I'm going to make a little model here. Let's say I've got 6 particles of water and I boil it. All right, so we know that as we boil it, those particles inside are going to be moving faster and faster and faster. They're going to be spreading out more and more and more until they turn into a gas, in which case they're going to leave. So in a model, I would probably draw a couple of those with arrows, of course. I just don't have much room. And I'd put arrows on these ones down here. But we can understand why there's less mass at the end. Because that liquid water turned into water vapor that left the system. Okay, so a gas is involved again. What's a gas? Water vapor. Is it an open system? Yeah, because we don't have this this water covered. Now, if we covered the water or something, then it might be different, but we didn't. Okay, we have a closed can of Coke. Okay, it's really cold. Okay, so the particles outside, they're moving fast. They're at room temperature, moving around, zipping around everywhere, bouncing off the walls of the container, of course. If they weren't, they wouldn't be causing any pressure, and the can would explode, actually. But they're zipping around, bouncing off the can. But since the can's cold, every time they bounce off the can, they transfer energy to the can. When they transfer energy to the can, that means they've lost some energy now, which means they're going to be moving slower. And when they move slow enough, eventually they're going to turn into liquid on the side of the can. So water vapor condenses onto can as liquid water. So that's liquid water on the outside of the can. That's what it is. It's cooling. Now here's another example of talking about Is there a gas involved? Yeah, there's a gas involved here. So if we were talking about conservation of matter, what would we expect to happen to the mass of that can of Coke from beginning to end? Well, this is another example. We find the mass of the cold Coke can. Since there's water vapor that's going to be turning into liquid water on the outside, the mass should increase a little, okay? Because there's now liquid water on there that we can find the mass of with a balance that wasn't there before. It was in the air. And I guess that's the idea. A balance can find the mass of solids and liquids, but a balance can't find the mass of a gas, really, at least not easily, okay? So can matter be destroyed? No. We just went over that in a bunch of questions. Matter cannot be destroyed. Can't be just appear from nowhere either. What we can do is during chemical reactions, which I abbreviate RXN, we can rearrange particles, okay? Kind of like Lego blocks. I have a stack of yellow blocks and a stack of blue blocks, and I can rearrange them and put them together so that maybe one stack becomes, or both stacks become yellow and blue. We can have open systems where particles can leave, but not destroyed, okay? They're still somewhere. They're just not in the system anymore. Um, okay, so we're going to do particle diagrams for solid, liquid, and gas. Real basic ones too, because I don't have a lot of room here. So here's a solid. I'm just going to put some dots close together. Maybe 6 of them. And when we do this, we've got to show that we understand that all particles are in constant motion. So even in a solid, these particles are moving slightly. They're moving slowly and they're close together, but they're kind of just jiggling back and forth. So we'll use these, what we call motion lines that look like quotation marks. I even put a couple in between the middle here. Okay, so the particles are kind of vibrating back and forth. That's a solid. Okay, we talked about density of the phases as well. So these are dense because they're close together. And like I already said, moving slowly. All right. Liquid, let's say I still have those 6 particles, but now they're going to be a little more spread out. Okay? And now in a liquid, the particles do actually change place with each other and move around a little bit, so I will draw arrows on those, just random directions. Not big ones, though. So these are kind of medium speed, medium spacing, medium density. And then we've got a gas, okay? And gas particles are going to be really spread out. So this is the least dense, most spread out, moving the quickest. So I draw big arrows on them, again, random directions. Okay, and that would be a gas. All right, so substances, solid, liquid, gas will have particles with the strong. Which one will have particles with strongest attractive forces? So attractive forces are only going to be strongest when particles are close together. So particles are strongest in a solid, a little weaker in a liquid, but still there. And in gases, they're almost non-existent. Still some, but very, very weak. All right. Provide examples of ways that particles can change movement. So they can collide with each other or objects. And we can also change their speed. And we do that by changing the temperature. Okay, we can also maybe affect their motion by allowing them less room to move around, which would be volume. We can also affect their motion by adding more particles, okay? Because then they're going to be bouncing into each other more. All right, back to the collision part. What causes pressure? It's the number of hits. So how often does something hit something else? So these particles in a gas flying around everywhere. Okay, how often are they colliding with things? Collisions. That's what that is. Okay, so a thermometer works on two concepts, so we got to think about energy transfer and thermal expansion. So if we have a thermometer in a cold environment, and then we have one in a hot environment, okay? So in the cold environment, the particles are going to transfer their energy to the air, all right? As those as those cold particles are bouncing off the thermometer, which has this liquid in it, energy is going to be transferred from the particles to the air, which means they're now going to have less energy in there, which means they're going to move slower and come close together. They're going to constrict, get closer together. Okay, so we'll have a lower level here, and we'll have a lower reading on the thermometer. But when it's hot, the particles outside have more energy, and they're going to transfer that energy in to the liquid. Okay? That energy goes into the liquid, they're now going to move faster, they're now going to spread out, and they're going to expand, which means the level of the liquid is going to go up, and that's going to give us a higher reading. And that's how a thermometer works. Energy transfer, either from the liquid to the air, or air to the liquid, or whatever the substance is we're measuring the temperature of. And thermal expansion, when things get warmer, they move faster and expand. The opposite is true when they get cooler. We reduce the temperature of a substance, the particles get closer together, and they get more compact. Okay? Which means more dense. Okay. What does temperature measure? So really what temperature measures is that average kinetic energy. So I said this earlier in the video. The kinetic energy is really talking about the speed of the particles. Okay, so how fast are those particles moving? And we develop a scale that goes along with average kinetic energy. So Kelvin scale directly related to average kinetic energy. Okay. So Celsius, I mean, temperature changes regardless of what scale you use. A liquid's going to expand or contract depending on if it's hot or cold. Um, but what we do is we make this Kelvin scale. It doesn't have any negative numbers because what we do is we take the lowest possible temperature, Celsius, and add 273.15 to it. And so what that assures us is if the lowest possible temperature is 273.15, it means the lowest possible temperature we can have for Kelvin would be 0. So we don't have any negative temperatures. All right. How does a straw work? It works on differences in pressure. Okay, so we've got a glass, and we've got a straw in there, and we've got a liquid. All right? Put blue for the liquid. All right? So what happens is all this air above the straw is pushing, and above the liquid in the cup, is pushing down on it. All right? And so if we put our mouth on there, if we can make it so mouth has less hits, less pressure than outside, the atmospheric pressure, what that will actually do is that atmospheric pressure will push down on the liquid and push it up the straw into our mouth. So that's the main concept. We have to have less pressure in our mouth than the atmospheric pressure. All right, so some different factors that can affect the pressure of a gas. The temperature is one. If we increase the temperature, particles move faster and they hit the walls of the container more often, causing an increase in pressure. If we cool them down, less hits, less pressure. The volume. If the particles have less space to move, so lower volume, they're going to hit the walls of the container more often. Okay? So volume is less, the pressure would be increased. All right? If the volume was greater, then there's more room and the particles won't hit the sides of the container as often, the pressure is less. With temperature, remember temperature and pressure are a direct relationship. Okay? So if one increases, the other increases. If one decreases, so does the other. All right? We can talk about even the amount of gas. Okay, so if I increase, we call this N. So if I increase the amount of gas, particles are going to be hitting the walls of the container more often. If I decrease the amount of gas, particles are going to be hitting the sides of the container less often. We can even talk about the external pressure because that always equals the internal pressure when we have a flexible container. Okay, what are the units used to measure volume for a solid, a liquid, and a gas? Okay, so solid. We might measure with a ruler 3 different sides, like I said. Length times width times height. If we've got a regular solid, a regular shape like a cube or a rectangular solid, whatever you want to call it, if we can take an easy length times width times height measured in centimeters, we're going to end up with centimeters cubed. Now sometimes we get a solid that's weird shaped, doesn't have an easy length, width, and height to measure. In that case, we'll use displacement and put it in a graduated cylinder. Let me block this off so we're talking about solid here. And then in that case, I can do it in milliliters as well. Liquid, we'll just put in a graduated cylinder and measure it in milliliters. And then a gas, typically we measure that in a little bit larger units like liters, but it's related to milliliters, but liters. Also important note, something that we covered during the semester, remember the relationship between cubic centimeters and milliliters. 1 cubic centimeter is equal to 1 milliliter. So these terms right here are pretty much just interchangeable. If I had something that had a volume of 30 cubic centimeters and I plopped it into a graduated cylinder to see the amount of displacement, the amount of displacement should be 30 milliliters. All right, how is atmospheric pressure related to altitude? This is another inverse relationship. Okay, so if altitude increases, so the higher we go up, the less air there is above us. Okay, which means the atmospheric pressure, ATM pressure, would be less. All right, if I go lower, like down to sea level, the pressure is actually greater because there's more air above us. So the atmospheric pressure is different along the coast than it is, much different along the coast than it is in, say, Denver, which has a higher altitude. Okay, work conversions. So you're going to be given some uh, some comparisons, some things we talked about. I told you guys if we start with just the basic 1 atmosphere, we talked about standard temperature and pressure, by the way, STP, which represents a gas at 0 degrees Celsius. That's a standard temperature, and 1 atmosphere of pressure. Okay, so we start with 1 atmosphere. We could say that's equal to 760 millimeters of mercury, which is the same thing as 760 torr, which is also equal to 101.3 kPa, which is also equal to 14.7 psi. Okay, so there's some different units we can use for pressure. We want to use our knowledge of comparisons to solve these problems. Now, the way I do it is I say, take what's given to you and always start your equation with that. Put it over 1, too, so that you remember it's on the top part of the equation. All right, so what's given to me is 3,000 millimeters of mercury, so I'll just put that over 1. I'm going to multiply this by a conversion factor. So I'm going to do times, and then I'm going to do a line, and I'm going to put some units over here, and I'm going to use these relationships up on the top. Whatever unit I have here, I want to put that same unit down here. And whatever they're asking me to find, in this case kPa, I want to put that on top, okay? So I'm going to use my relationships on the top there to plug in the conversion factor to solve this problem. So my numbers at the top are 101.3 kPa per, or for every, 760 millimeters of mercury. So now what I'm going to do is I'm going to multiply across the top, and I'm going to get some kind of top answer up here. I'm going to multiply across the bottom and get some kind of bottom answer. I can do that right now because it's just 1 times 760. That's just 760. Now I'm not going to write millimeters of mercury, though, because since I have millimeters of mercury on the bottom and on the top, they cancel each other out. My top answer I'm going to have to use a calculator for. So I'm going to take my calculator. I'm going to plug in 3,000 times 101.3, and I'm going to get 303,900. And I do have units left on top. I have kPa's. Okay? Now, to get my final answer, I'm just going to do division there. Okay? So I'm going to take that 303,900. I'm going to divide it by 760. And that's going to give me a final answer of roughly 400. And the units, like I said, are still there, kPa's. That's my final answer. So looking back at this, it's telling me 3,000 millimeters of mercury is the same thing as 400 kPa. All right? Just different units, that's all. It's like measuring speed in miles per hour or kilometers per hour. You're going the same speed, it just depends on what units you're using. All right, so same way to solve this next one. I'm going to start with what's given, 87.9 atmospheres. I'm going to put that over 1 so that I remember that's on top, okay? And so I want to put ATMs on the bottom of this one, and I'm going to put torr on top. This is probably going to be a pretty big number, all right? So torr, using my relationships, there are 760 torr for every 1 atmosphere. So multiply across, get your top answer, get your bottom answer. My bottom answer is just going to be 1 times 1, and the atmospheres have canceled out. My top answer, though, is going to be kind of big. Let's see, 87.9 times 760. 66,804. And I still have the units torr up there. And it's just over 1, so that's actually my final answer. So 87.9 atmospheres is equal to 66,804 torr. All right? 26.11 psi. That's going to be my start. Put it over 1, right? Times. I want psi on the bottom so that it'll cancel out. The units I want on top here are kPa. All right? Use my relationships. There are 101.3 kPa for every 14.7 psi. Psi cancels out. All right? So multiply across, get a top answer, get a bottom answer. Bottom answer is just going to be 14.7. The top answer is going to be 26.11 times 101.3. And so that's going to be 2645, roughly. I'm going to take that number, I'm going to divide it by 14.7, and I'm going to get 180. My units I have left, should have wrote them here. There's your final answer. Now, I do recommend that you kind of set up some of your own practice problems. Pick a couple different units. Say if I have this many of this unit, how many of this unit would it be? Make some problems for yourself, because I know if students work along with my videos, sometimes it gives them a false sense of confidence, and then when they have to do it on their own on test days, it's a little more difficult. So practice a couple more of these on your own at home. 26, make a graph that shows a relationship between pressure and volume for a gas at a constant temperature. Would this be an inverse direct, or inverse relationship? So, pressure and volume. All right. So if we graph volume and pressure, we know it's going to go downhill. And this is actually just kind of distinguishing between, they're both downhill graphs, okay? But if the volume increases, the pressure will go down, down to a certain point where it'll kind of level off, okay? Only going to get down to a certain pressure. And so it's not going in a straight line necessarily. So this would be an inverse direct. So that's why we just call this relationship an inverse relationship. All right? It's not going to do that. It'll do this. Relationship between volume and pressure. Okay, so conversions. We know that if we take degrees Celsius, the coldest possible temperature is negative 273.15 degrees Celsius. We know that's equal to absolute zero in Kelvin. That means if I just add 273.15 to whatever the Celsius temperature is, I'll get Kelvin. So in this first one here, they're giving me Kelvin. They're saying it's they're giving me Celsius. So I'm just going to add 273.15 to that. And if I do that, I'm going to get 83 plus 273.15, and I'm going to get 356.15. Always put your units in there. Always, always, always put your units in there so you remember what you're doing. This is asking you to go the other way. Okay, so I'm actually, in this case, I'm going to have to subtract the 273.15 from 300 to find out how many degrees Celsius. So if I do that, 300 minus 273.15 is going to come out to be 26.85. And we are changing it to degrees Celsius. All right. No, it's a long video. We're almost done here, though. So we said we don't have to know what the gas law is named, so we can ignore that part. This is where we use those IFE charts. Okay, so I make a 4x4. And on the top, I'm just going to put those different factors affecting a gas, like pressure, temperature, volume, the amount of gas. All right, and the left side, I'm going to put IFE. This is for initial, final, and effect. Okay. So, I'm going to erase that to see if I can use the same chart for each problem. All right, so we know we can ignore that. All right, so what I see here, I've got gas, 5 liters of a gas. I have to know that liters is volume, okay? It's at 1.08 atmospheres. I have to know that atmospheres are pressure, okay? So those are my initial conditions. So I have 5 liters of a gas, that's volume. And write your units in here as well. Always write your units. And the initial pressure is 1.08 atmospheres. Doesn't say anything about temperature or amount of gas yet. I might be able to just cross those out. What pressure is obtained when the volume is 10 liters if the temperature stays constant? So they're telling me temperature stays constant, so I can ignore it. They're also not saying anything about the amount of gas changing, so I'll cross that out as well. All right? It says what pressure, so some new pressure, some final pressure, I'm going to put a question mark. I don't know what that is obtained when the volume is 10 liters. Okay? So what I first want to do is look at what I have, the volume. Initially it was 5 liters, and it changed to 10 liters. So down here in the effect row, I'm going to make a note that the volume increased. All right, now I want to make a prediction over here. What should that mean for the pressure then? If the volume goes up, what should happen to the pressure? Well, if the volume goes up, there's more space for the gas particles to move around, meaning they're going to hit the sides of the container less often, which should mean less pressure. Okay, so when I set up my equation and try to solve for this, that should all make sense. So when I set up the equation, always start with the one that has a question mark under it. That's going to be your start, similar to what we did up there converting between different units for pressure. Okay, so I'm going to take that start and put it over 1. I'm going to write times, and here I'm going to use my conversion factor. Now the conversion factor is going to be the variable that I have both numbers to, which is volume over here. Okay. And what I'm going to do is I'm either going to leave it like it is, 5 over 10, or I'm going to flip it upside down, 10 over 5. Well, I know the pressure should become less. So if it should go down, I should put the lower number on top. So in this case, I'm going to put 5.00 liters on top, put 10 liters on the bottom. And now I've got liters on top and on bottom again, so those cancel. The only units I have left are atmospheres, which is right, because that's what I should be finding is the new pressure. So I'm going to multiply across the top, and that's going to give me 5.40 atmospheres. Multiplying across the bottom is just 1 times 10. That's just 10. And at the end, I'm going to divide, so I should end up with an answer of 0.540 atmospheres. Okay? Does that make sense? So the volume, and don't think of like how much it goes up in terms of adding or subtracting. Think of multiplying by factors. So the volume actually doubled. And since I know that the volume and pressure are an inverse relationship, it makes sense that if the volume doubles, the pressure should go down by half. Okay? And that's actually what it did. It was 1.0 atmospheres. It went down by half, down to 0.54 atmospheres. So that makes sense. All right? Gives me a little confidence in my answer. All right. Let's see here. Not really helping me as much as I had hoped. All right. So make a new chart for my next problem. All right. So number 29 here. All right. Here's something to remember. Whenever you do these types of problems and you get degrees Celsius, change it to Kelvin. Just get used to it. All right. So if I've got 25 Celsius, 25 degrees Celsius, that's actually going to be 273.15 plus 25. It's actually going to be 298.15 Kelvin is what I want to use. All right, so that's going to be the initial temperature. And it says it occupies 3.60 liters. Again, liters, that's for volume. Okay. At a pressure of 1 atmosphere. Oh, I remember this silly problem. Made me change Kelvin. I don't think I need to. No, I don't, because here's what it says. What will be its new volume? So the final volume, question mark, if I change the pressure to 2.5 atmospheres and the temperature remains constant. Okay, that means I can ignore this column. That means this over here that I didn't need to do. I could have just crossed it out. It also doesn't say anything about the amount of gas, so I can cross that out. All right, so in this case, pressure is what I have both numbers for, and I see that the pressure is increasing. And we just did a similar problem between volume and pressure. One goes up, the other goes down, right? So if the pressure is going up, that must mean that the volume is going down. So I'm always going to start with one with the question mark over it. So 3.60 liters. Put it over 1. And I know the volume should go down. So again, I'm going to put the lower number on top in this conversion factor over here. I'm going to put 1 over 2.5. Like that. Atmospheres will cancel out. And so if I multiply across the top, I'm going to get 3.60 liters. Multiply across the bottom, I'm just going to get 2.5. And then just divide that. I'm going to get 3.6 divided by 2.5. And voila, I've got 1.44 liters. Does that make sense? Okay. Started at 3.6, went down to 1.4. We know it should have gone down. The pressure changed by more than twice, so the volume should go down to less than half, and it did. All right, so that makes sense. All right, number 30. So again, I can do my IFE chart if I wanted to. I'm just going to write them down here. It's saying gas occupies this volume at this pressure. All right, what will be the new pressure if the volume becomes this? All right. So really, it's just I have both. I know that the initial. Let's see what I have here. I have initial pressure and volume. So initial pressure is 0.860 atmospheres, and the initial volume is 11.2 liters. What will be the new pressure if the volume goes to 15 liters? So the volume is going up, the pressure should go down. So if I take my 0.860 atmospheres, and if the pressure should go down, let's put the lower number on top, 11.2 liters over 15 liters. And I should get an answer of 0.860 times 11.2. That comes out to 9.62, 632 atmospheres. Bottom is just 15, so I'm just going to divide that by 15. It comes out to be 0.642. So it went down. Does it make sense? Volume increased a little bit. The pressure should go down a little bit. Seems good to me. All right, 31. All right. Okay. So we have a sample of gas has a volume of 12 liters, a pressure of 1 atmosphere. If the pressure of gas is increased to 2 atmospheres, what is the new volume of the gas if the temperature stays constant? So temperature stays constant, and the amount of gas stays constant, so I can ignore those. I'm just focused on the volume and pressure again. And like I was saying, them changing by the same factors, like if you wanted to do an IFE chart for this, by all means, feel free to do it. But I noticed something here. I noticed that this is 1 atmosphere, and it's being increased to 2. It's doubling. So if that doubles, that means the new volume should be half of what it was. Should go down to 6 liters. Go ahead and set up your IFE chart and solve it and see if I'm right. All right, 32, 3.75 liters of a gas in a flexible container, so the volume can change, is heated from 30 to 55. What would the new volume be, assuming the pressure has remained constant? So in this one, we are going to ignore the pressure. Does it change in any certain factor that makes sense? Not really. So I got my pressure, temperature, volume, my amount, my IFE here. All right, pressure remains constant. Amount of gas remains constant again. Okay. So we do have temperatures. They are involved with the problem. Let's go ahead and change those to Kelvin. So if I add 273.15 to this, I'm going to get 303.15 Kelvin. This is going to become 328.15 Kelvin. So those are my numbers there. All right, so this would be my initial. It's saying I'm starting at 303.15 Kelvin. So let's put that down for our initial temperature. And my final temperature, I'm heating it to 328.15 Kelvin. All right, so the temperature is increasing. And the volume initially was 3.75 liters. So if I heat that 3.75 liters in a flexible container, what's the volume going to be? Again, it's a flexible container, so initially the particles are going to start moving faster. They're going to be hitting the insides of the container more often than the outside, which means for a little bit, the internal pressure will be greater than the external pressure. But like we know, in a flexible container, when it's all said and done and the walls of the container stop moving, the internal pressure will be equal to the external pressure. All right, so I'm going to start with my 3.75 liters for volume because that's got the question mark under it. Let's go ahead and put that over 1, right, times, make a line. Now our effects, if the temperature increases, like I said, the particles inside should be hitting more often, forcing the walls of the container outward, meaning the volume is going to increase until the pressure inside is equal to the outside. Okay? So if the volume is going to go up, in this case, I actually want to flip this conversion factor because I want the larger number on top. I hope you're watching all this because all those volume and pressure ones, it looked like you could just write it down the way it was, but more often than not, when we have these direct relationships like between volume and temperature and pressure, you're going to be putting the final number on top. So I'm going to put the 328.15 Kelvin on top, and I'm going to put the 303.15 Kelvin on the bottom. So the Kelvins cancel, and now we can calculate a top answer and a bottom answer, and then divide. So on top, I'm going to have 3.75 times 328.15. And that comes out to be 1230. I'm just going to leave it. I'll put it as 1231. All right, so 1231. My units are liters. On the bottom, I'm going to have 303.15 K. All right, so I'm going to take that 1231. I'm going to divide by 303.15, and I'm going to get 4.06. So I want to check, does this make sense with what I had? We predicted the volume would go up. The temperature went up a little bit. The volume should go up a little bit. It did, so cool. And finally, we're at our last problem. Number 33. So I've got a gas in a rigid container. The volume can't change. Okay. The initial pressure they give me the initial temperature. They say, what should the pressure be if the container is cooled? All right, down to 7. All right, so I'm going to change these to Kelvin first of all. So this is actually 293.15 Kelvin, and this one would actually be 280.15 Kelvin. All right. IFE chart. go. Rate, pressure, temperature, volume, amount of gas, I, F, E. All right, so I've got a temperature. I've got two values for temperature. This is going to be my initial, what I'm starting with. So I started at 293.15 Kelvin. I'm cooling it to 280.15 Kelvin. So the temperature is going down. All right, I have an initial pressure of 140 kPa. The volume is staying constant. It's in a flexible container, and we're not talking about the amount of gas, so I can ignore those two columns. What is the new pressure? Okay, so pressure and temperature in a non-flexible container. I'm cooling it, which means the particles should be moving slower, hitting the sides of the container less often, which means the pressure should be going down. All right, so take the one that's by itself, the 140 kPa, put it over 1, multiply by a conversion factor that's going to make it go down. Okay, so again, if we look at this over here, I want to have the smaller number on top so that it goes down. So I'm going to use 280.15 on top. And I'm going to put 293.15 on the bottom, like so. Kelvins cancel. So my top answer is going to be 140 times 280.15. That's going to equal 39,221 kPa. That's going to be over 293.15. That's going to be 133.8, 134. Sorry, I skipped a step. Does that make sense? Makes sense for a couple reasons, actually. I think. Well, we know that the temperature went down. The pressure should have went down a little bit. Yeah, I guess that's the only reason. Makes sense. But that's the exam review.